Hello everyone, again welcome back to the latest lecture session. So in the last session we were looking at designing the relevant PRB, right? Designing the PRB in meaning we are trying to get the or estimate the thickness of the PRB required so that the relevant concentration of the compound, let's say, will be decreased to the relevant regulatory standards or such, right? Or whatever design value you want to look at, let's say, right? So in that context, obviously we need to understand, let's say, how the concentration or the compound is going to be affected within that reactor, right? So in that context, we had to look at material balance or mass balance. So thus we, in the previous class or session, we looked at the relevant material balance equation, and we looked at two kinds of equation, one the fundamental mass balance equation, right, and the other one applicable to macroscopic systems. So typically when we say macroscopic systems, we apply that equation when the concentration of the compound throughout that particular reactor or the volume or control volume is the same. But let's say groundwater, let's say, and you take a control volume, let's say, you typically obviously notice that the concentration changes with distance. So in that context, we also looked at the fundamental material balance equation. So what were the two equations that we had? So for the macroscopic scale, we had something like V dC by dt. This was giving me an idea about the accumulation of the compound is equal to Q in C in, so mass coming in, right? This will give me an idea about mass coming in per time obviously, and Q out, C out. This will give me an idea about mass going out, plus volume into rate of formation minus rate of loss, as in reactions leading to formation of that particular material and loss of that particular material, right? And this is our particular case for the macroscopic systems. And obviously we also looked at the case for microscopic systems, and that was equal to plus U dC by dx. So in this context, we considered that the concentration was changing only along a particular value, not value, pardon me, a particular dimension or along x direction in this particular case. So again, what is this giving me an idea about? And if we will just try to relate that to this equation out here. So U dC by dx, right? dC by dx, if I try to understand that in terms of del C by del x, what is that going to be equal to? C2 minus C1 by x2 minus x1, right? In a way, again, it is coming, it is similar, not in a way, it is similar to what you have out here if you take these terms out to the left hand side, right? Again, this is giving me an idea about the mass going out minus the mass coming in, right? Again, let me finish this equation. It is going to equal to the diffusion relevant term, diffusion coefficient, into the second derivative here, right, plus rate of formation minus rate of loss, right. So this was the case when we considered that the velocity of flow of that particular fluid was constant and the flow was only in one direction, let's say, and also we assumed that diffusion or dispersion is also relevant only in one direction. Obviously if it is relevant in the other directions, you will have the y and z terms, right. Again, this obviously is the fundamental mass balance equation slightly tweaked to be able to apply that to the relevant groundwater though, right. But again, we simplified this further, and for our PRB case, right, what did we come up with? We also looked at steady state. So when we look at steady state, this particular term is 0 obviously. So we have U dC by dx is equal to rate of formation minus rate of loss, assuming that there is no the diffusion term is negligible inside the PRB, right. So we are now trying to get at what is happening inside the PRB. So my control volume is the PRB, right, my control volume is the PRB, and the relevant compound is the compound of interest here, right. So and this again transforms to dC by d theta, theta is the hydraulic retention time in this case, equal to rate of formation minus rate of loss. So one aspect is how do I get at this particular rate of loss. So in that context, we talked about conducting an experiment in the lab, right. So you have relatively similar reactive media, you will put the compound and measure the change in concentration with time, and then you will get a graph something like this. I have concentration here and time here, batch reactor, right. I have relevant media and the relevant compound. So I am going to write the concentration or have samples at different times, and I will have the measure the concentrations at those times, right. And then I can fit a model by regression and get the relevant k value, right. So I can use this k value then for my particular PRB case, right. So this is applying the mass balance for the batch reactor, and then I will get the K value, and then I will apply that in my plug flow reactor, right. So, one aspect that needs to be kept in mind is that we have our rate of loss is equal to rate constant times A is area per volume, right, area of 0 valent iron per volume of water times the concentration of compound, right. So, here I am using the K that I am measuring in the lab, right, but typically what K am I measuring? I am measuring the pseudo first order rate constant, it is not the true rate constant I am measuring, as in because I am going to put in a lot of 0 valent iron, let us say, or a stoichiometric excess of 0 valent iron. Typically I can express this equation as K dash times C. So, this as you see is not a second order as we see here, but a pseudo first order, right, it is a pseudo first order. So, typically in the lab we end up measuring K dash, right, and not the actual rate constant. So, when you are trying to use the same K dash for the actual case of PRB in the ground, what issues should you be keeping in mind? As in we know that K dash is equal to rate constant times A, and you know that it is equal to specific surface area times the concentration of the 0 valent iron. So, if you do not use the same kind of 0 valent iron or the reactive media in your batch experiment in the lab and in the actual case that you are trying to estimate here, then obviously there will be issues. So, you need to keep that in mind. So, if you use different kinds, the surface area per what do we say mass of 0 valent iron will be different, right, or as in let us say a simple example, let us say because it is relatively cheap, let us say I get some particular bigger size particle for my particular lab experiment, but in the actual PRB let us say I use relatively smaller size particles. So, in that constant case AS is going to be different, right, because the surface of the 0 valent iron available per mass of 0 valent iron is going to be different, and so you can't directly use that K dash from the lab in the actual field or for the actual field design. You will need to be able to adjust that, right. Same case with concentration of 0 valent iron, whether it is the same or not in the lab and the actual condition. So, that is something you should keep in mind because we are actually estimating K dash and not K. So, in that context obviously how can I calculate concentration of 0 valent iron? So, what is that equal to? That is the mass of 0 valent iron per volume of water, let us say. I want to be able to calculate this. So, how do I get this? If you look at this, we have 1 minus porosity times divided by porosity into the density of that 0 valent iron, let us see. And what are the, how does this transform into, what is porosity? Volume of pores by total volume, and thus what does 1 minus porosity give you an idea about? Volume of solid, right, by total volume. Volume of solid obviously meaning that will be the volume of 0 valent iron. So, density of 0 valent iron, what is that about? Mass of 0 valent iron by volume of 0 valent iron or the solid, right. And what is that going to be equal to? Let me just write that out here, right. That is going to be equal to, I am going to cancel out the total volume here, right. So, it is going to be equal to volume of solid by volume of pores into mass of 0 valent iron, mass of 0 valent iron by volume of the solid which is 0 valent iron, right. So, here two aspects obviously, what do we understand from volume of pores, right. So, in a PRB obviously the pores are filled with water, so it is volume of water. Volume of pores in this context would mean volume of water. So, cancelling these two terms, the 0 valent iron and solid are the same in this context. So, again obviously porosity refers to the porosity of the 0 valent iron, right. So, I end up with mass of 0 valent iron per volume of pores, which is nothing but volume of water in the PRB. So, that is the concentration of 0 valent iron, right. So, what do we, how can we calculate that? 1 minus porosity of 0 valent iron divided by 0 valent iron into density of 0 valent iron gives you an idea about the concentration of the 0 valent iron, right. So, that is one aspect again that you need to keep in mind. So, what do I have now? I have the rate constant, or let us say pseudo first order rate constant, yes, and I can now get the relevant design done. So, dC by d theta is equal to minus rate of loss here, right. So, again what is that going to be equal to, or how can I transform that into now? So, if I integrate and so on and so forth, Ct by C naught is equal to e to the power of minus k theta. K here is the pseudo first order rate constant, right. Obviously, rate of loss is k dash times C, right. It is not C here, C at theta times C naught is equal to e to the power of minus k dash theta. So, just plugging in the relevant what we say values here, dC by d theta is equal to minus k dash C, right. dC by dC, pardon me, dC by C is equal to minus k dash times d theta, and again integrating that, this is what I end up with, right. So, what am I trying to calculate here? The whole point is I am trying to calculate the thickness, right, thickness of PRB. So, how will I so I have one particular equation from the relevant mass balance here, right. C at when it enters the system is C naught, C when it leaves the system is C theta is equal to e to the power of minus k dash theta. So, I can measure the concentration coming in, which is I have C naught, I know the concentration that I want when the compound leaves the system, C theta, right, and I already have k dash, right. So, what is it that I am trying to calculate? I am trying to calculate theta here, right. So, I am trying to calculate theta here. So, from this particular equation I can get theta here, right, and what is theta giving me an idea about? The hydraulic retention time, or in this context how much time is the relevant compound spending inside the PRB, right. So, that is what it is giving me an idea about, right, and as we know theta is equal to volume of that particular system by the flow through that particular system, right. So, what is the volume of that particular system now? It is going to be equal to the porosity of that particular PRB, right, times the cross sectional area of the PRB times thickness, let us say I will use the term, okay, I will write it T for thickness. So, this is the volume of the PRB times porosity of the PRB is the volume of water obviously, divided by the flow of that particular water through that particular PRB, right. So, from here as you can see, what do I have? I already have porosity, I already have hydraulic retention time, I calculated that out here. I have the cross sectional area of the PRB, right. What is the length and height of the PRB equal to? It is going to be dependent upon the size distribution of the relevant plume, right. So, the plume is let us say 100 meter wide and 2 meter thick, not thick, but let us say height, let us say. So, relevant dimensions of the relevant PRB, right. So, from that I can get the cross sectional area and I know the flow rate, let us say, and now what can I calculate? I can calculate the thickness of PRB. So, that I can calculate here, right. So, that is something I have, and in this context one minor aspect though, how can I get Q though? So, for example, if I have Darcy's velocity, Darcy's velocity let us say, right, and what is that going to be, how do I get Q from Darcy's velocity? Into the cross sectional area though, right. So, into the cross sectional area, but if I have seepage velocity as in, how is this different from the Darcy's velocity? You can think of Darcy's velocity as in, this is in the context of groundwater obviously. So, let us say the average velocity of that particular fluid for that particular cross sectional area, let us say, right. So, if this is the side view and the groundwater is flowing through this particular system and this is my cross sectional area, or let me draw the other side view, and the groundwater is going in this direction towards the screen, okay, or into the screen, let us say it is going into this. So, if this is the cross sectional area, that is what I am talking about here, the area of this particular system, cross sectional area times Darcy's velocity will give you the flow of groundwater, right. But if I do not have the Darcy's velocity, but the seepage velocity, what is seepage velocity about? So, here in groundwater you have soil and then the pores, right. Where is the groundwater flowing through? Through these pores, right. So, the velocity of that particular groundwater through these pores is called the seepage velocity. So, if you obviously think about it, the seepage velocity is going to be higher than the Darcy's velocity, right. So, when you are writing it down or trying to calculate Q, you need to try to understand, do you have the Darcy's velocity or the seepage velocity. Let us say if this is the seepage velocity and times cross sectional area, then I will end up with a higher value obviously, right. So, I will need to multiply that by the porosity of that particular aquifer. Keep in mind, this is not the ground PRB, but for the aquifer. So, why did we look at that again? How do I get Q? The flow of the groundwater, right. How can I get that? I can get that by multiplying the Darcy's velocity into the area, relevant area, or if I have the seepage velocity, I need to obviously look at it with respect to, or try to modify it with respect to the porosity of the aquifer, right. So, these are aspects that you need to keep in mind. So, obviously from this context we come up with the thickness of the PRB, right. So, obviously if it is funnel and gate, right, still the relevant calculations are still the same, because we are just considering volume by Q, the volume changes or the cross sectional area changes, right. So, with that I guess I will move on to the relevant aspect with respect to the case study, right. So, until now we have looked at the relevant technical aspects. So, let us look at in a bit more detail where this PRB was applied, at least initially anyway. You know, now it is relatively more widely used for most purposes out there. So, the case study we are going to look at was one of the initial case studies done on site, actual site conditions. So, they obviously conducted some laboratory experiments to get the data, chose 3 different kinds of reactive media, right, and they put in 3 PRBs in the groundwater, and this groundwater was contaminated with uranium, right, say radioactive, and other heavy metals too, but mostly they were concerned with removal of uranium from the contaminated groundwater, right. And then they looked at the relevant efficiency of removal and then other parameters, and I believe they monitored it for a year or 2 years, so that they could use this particular case study to be able to judge, let us say, whether PRB is worthwhile for what we say wide scale or full scale emplacement or such, or usage, pardon me, right. So, let us look at that case. So, here the reference that I am going to look at is you know, all the data that I am going to present or figures are not what I developed, they are from this particular document available in the public domain. It is the field demonstration of PRB to remove dissolved uranium from groundwater, and it was in Utah, and it was run from September 1997 to 1998. It was developed by EPA and USGS, right, Utah in the US. Okay. So, I think I have that particular you know document here. So, this is the relevant document that you can get, let us say, if you you know, from the relevant internet, it is in the public domain again. So, we are going to discuss the aspects, you know, that were presented in this particular document here for our case study now, right. So, let us go back to where we are here. Okay. So, this is the reference here. Again, some background. So, looks like uranium, let us say contamination can occur due to multiple what do we say sources. One source is obviously if I let us say have a uranium source and I am digging for uranium or a uranium mine, let us say, obviously the relevant waste or such, or you know, the leachate, let us say, I can have the relevant uranium contamination or leading to uranium contamination. But looks like you know, there is another case that is relatively more you know the major source, let us say, for uranium contamination in groundwater. So, let us say you have other metals or ores, and you are processing these ores or trying to upgrade the relevant quality of this particular ore. You also have uranium in these particular ores. So, when you are processing them, let us say, you are going to have contamination of the relevant site with uranium, and that is the case here. So, it looks like in the 60s or 70s, 1960s or 70s or 50s rather, pardon me, they had what we say ore processing units or ore upgradation units in this particular vicinity in Fry Canyon in Utah, right. And at that time they had what do we say, obviously uranium tailings, let us say, from processing the relevant ores, and from that particular tailings they now had contamination of the relevant groundwater and the soil with uranium among other heavy metals, right. But they were primarily, or they, as we are going to look at, were primarily concerned with heavy metals now, right. So, in that not heavy metals, pardon me, with uranium, yes. And then what they do, they conducted some lab experiments, let us say, on a huge number of what we say types of reactive media, then chose that 3 kinds of process, you know, seem to be better, as in one with respect to adsorption by bone char, I believe, right, and also precipitation or adsorption by amorphous ferric hydroxide, and then the third one as in the case that we typically have looked at until now, first reduction and then precipitation onto zero valent iron, right. So, three process they narrowed down their relevant options, and then they chose conducted the relevant experiments, chose one kind of material for each of these processes, put them in and went ahead with the analysis. So, let us look at that now. So, what do we have here? So, let us say Utah, it is near the Salt Lake. So, I believe you have particular rivers out here, and I think it is in the vicinity of these particular surface water streams, again just that it is in Utah, I guess, right. So, typically we are looking at the Fry Canyon site, and the relevant site out here, that is something that you can see here, and you can see the installed monitoring wells and such, yes. So, here Fry Canyon site in Utah, installation from 1997, and they looked at until 98. Typically we are looking at uranium, and the type that they looked at was not the continuous PRB, but the funnel and gate PRB, right. And the estimated cost was 170 or 1,70,000 US dollars, but keep in mind that this is the estimated cost. Let us see what the actual cost turns out to be and what are the reasons, I guess, right. So, let us move on. So, I believe I might have presented this earlier in my one of the slides or sessions, right. So, again they looked at the stratification and looked at the relevant geological units exposed in the Fry Canyon area. So, here you have the uranium tilings, typically the source of your particular contamination. So, two ways, either you have runoff coming in contact and directly, this is the Fry Creek somewhere out here, and you have the relevant aquifer, colluvial aquifer, and keep in mind we have sandstone underneath here, right. So, runoff from the tilings, contaminated runoff reaching the relevant aquifer or the Fry Creek, a small stream here, or again percolation, let us say, and then contamination of the relevant subsurface here, right. These are the relevant aspects, but typically they have a colluvial aquifer and then sandstone underneath it, right. And again keep in mind that there is a stream out here, yes. So, let us move on, and I think we looked at this particular graph. So, obviously they need to understand site characterization, that is what we need to do obviously, and obviously they need to understand the groundwater flow, right. So, for that obviously they had various control points, right, say, where from which they developed the potentiometric contours, right. They developed the contours, as you can see 5358, 5357, so on and so forth. So, I can try to understand the groundwater flow direction here, right. But obviously the case is that the groundwater flow direction changes, especially in this case, because you have a stream running nearby. Where is that? As you see, there is the channel out here, Fry Creek channel. So, this is the channel out here, right. This is the surface water stream that we are considered with. So, depending upon the rainfall and amount of rainfall, these contours can change, because typically let us say in the dry season the aquifer, let us say, or the subsurface aquifer here, or aquifer let us say, is going to, or the groundwater is going to flow from this aquifer to the surface water. That is how the surface water is recharged. But during rainfall the case can be that the surface water acts as a recharge for this particular groundwater here, yes. So, there are different aspects. So, I think this was in October 1996, and let us try to understand two cases. Once when we had low groundwater levels, as in during the relatively dry season, I guess, right, and this was July, and you look at the profile here in this zone typically, okay. And we will move on to the case when we had relatively higher what do we say rainfall, let us say, or during rainfall events, and now you see that the contours have relatively changed, yes. You can see the relevant difference here. So, obviously depending upon where I am putting in my PRB, right, I need to be very much considerate of these changes in groundwater flow direction. Why is that? Otherwise the groundwater flow or the flow lines can flow around the PRB, right. So, that is something I need to be considered with, and I think we did look at one of these relevant figures in one of the previous sessions, as in the case was that initially the surface water was, what do we say, recharging the groundwater. Groundwater was flowing in this direction, and then it was being contaminated somewhere out here. I think contamination source was somewhere out here or here, and then again the groundwater flow was reaching the aquifer. So, what is the key here? That this particular contaminant, due to the groundwater reaching the surface water stream, can then be transported to a wider area, right. So, obviously we need to limit this particular aspect, and let us see what we have. So again the concentrations seem to be as high as 16,000 ppb, but typically the average is 840 ppb, and keep in mind that the limit is 30 ppb for uranium in drinking water as per their standards. Okay. So again 16,300 was the maximum, but 840 ppb was the average, right. So keep in mind that again we talked about risk assessment, right. So let us say if a person in the initial classes we discussed risk assessment, if you remember, and in those classes if you remember we looked at calculating the risk based upon the exposure concentration. So as you see here, if I took my particular mean, let us say, or median here, I guess not the mean, median, and 840 microgram per liter, and just use that as a basis to calculate the risk assessment, the scenario would be much different from what, let us say, a person exposed to the maximum concentration would be, right. As an risk assessment calculated from median, as you see, will be widely different from the risk assessment risk posed when I calculate the relevant risk assessment or risk, pardon me, again from this maximum concentration. So these are aspects obviously we need to keep in mind. We are not going to go into that in detail now. Yes. So here we have concentration in ppb, right, and here we have different metals as I mentioned. These are in groundwater, and this is where we have uranium, and we have other heavy metals too. So obviously the median is somewhere out here, as we mentioned 840 or something like that. This is the logarithmic scale as you can see, and as you can see the maximum is around 16,000 or so, right. The maximum is around 16,000, the median is around 840, or what was the value please, 840, right. And obviously you have other compounds, some at relatively higher concentration than uranium, some much lower though, right. Again just a profile of they took the relevant samples from different locations, and only then can they get this relevant picture as in maximum, minimum, median, 75th and 25th percentile and so on, right. So that is what you see here. Let us move on. And also as you remember, I guess one of the aspects where, or one of the scenarios where this PRB is much relevant or worthwhile or would add to the advantage, let us say, or is advantageous when compared to the other options, is that you have adsorption of the relevant contaminant onto the soil, let us say, right, or when you have a non-aqueous phase liquid. Obviously you can't have a non-aqueous phase liquid in this case, but you can certainly have uranium adsorbed onto the relevant soil, right. So it will desorb over time. So just pumping out the water and treating that particular contaminated plume won't work, right, because the time required for pumping out the entire contaminant, right, will take time. Again, why is that? Because once you pump out the contaminated water, this particular uranium adsorbed onto the soil will now again desorb into the groundwater, right. So as you can see here, looks like here is the contaminated compound or source of contamination, the upgraded tailings, which have high uranium concentration, and here you have, what do we say, one particular sample location upstream of that particular source of contamination, and other sampling zones downstream of that contamination. So obviously as you see, upstream or far upstream relatively in the vicinity, I guess it is relatively low, but you see that the values, let us say, near that particular or downstream of that particular. So this is how, let us say, if the groundwater is flowing, let us say, yes, you see that the values are relatively higher out here, yes, 21.2 and so on. And again, what are these values? These are not the values in the groundwater, but these are the values adsorbed onto the soil. And keep in mind that I believe these are ppm values, not ppb. Let us just try to look at that. Okay, I think I have the relevant value later, but I think these are ppm and not ppb. For example, these were ppb, parts per billion, but the concentrations in the soil to my knowledge were ppm, but let us look at that. Okay, I do have the graph here. So well number, and here you see that parts per million, ppm, right. What do we have here? Uranium concentration from sediment adsorption and uranium concentration in groundwater. So as you see in each of these wells, especially the ones downstream, this is the one upstream, and these are the wells downstream of the contaminated site. You see that the concentrations in groundwater are relatively much lower compared to the concentrations adsorbed onto the soil, right. So keep in mind that when you are trying to take out the contaminant, you also need to take out the contaminant adsorbed onto, or both the phases. So the compound here is in the phase of or dissolved in groundwater, or in the aqueous phase, and also adsorbed onto the soil here, right. So again, these are aspects that we need to consider, but again looks like I am running out of time. So we will continue this discussion in much detail in the next session, and I guess that's it from me for today, and thank you.